Hey guys, I hope you all are doing good. In this lecture, we will be understanding what is proof by contradiction, right? So let's first try to understand what is basically proof by contradiction. It's just simply that I'm trying to contradict somebody's fact, and then I assume somebody saying is true, right? And then I say something or make some assumptions which lead to a contradiction, right? So let's try to understand the definition of what is proof by contradiction. I hope you all understand the word contradiction. I think we use it a lot in our vocabulary, right? So now understanding proof by contradiction is kind of very similar, so it shouldn't be that difficult to understand. So basically, assume negation of S is true, right? The first thing that we start with is whatever I'm trying to prove, I assume that the negation of it is actually true, right? So for example, let's say I'm trying to prove that a number is irrational, right? Now, maybe if I go the direct way, it would be difficult for me, or maybe I would not be able to prove it, right? So what I can do is I can assume that it is in fact rational, and then use the rational assumptions, right? Whatever assumptions I can make for rational numbers, and then try to reach a contradiction. So assume negation of S is true, right? Show that the assumption leads to a logical contradiction. Example 0 equal 1, or the statement that violates known facts. So what usually happens in a proof by contradiction is I assume the negation of S is true. So maybe I made the assumption that a number is rational, whereas I'm trying to prove that it is actually in fact irrational. But when I make those assumptions, and when I try to solve the equation or try to go ahead, I usually, what happens is that you come to a point where there's a contradiction, right? And that contradiction might be that you're violating some known facts in mathematics. It could be something, it could be maybe you come up with a zero in the denominator value, which is not possible, right? Or maybe you come up with something like 0 equals 1. So that's the basic point. If you reach this contradiction, then you can note down that there's this contradiction. And finally, conclude S must be true because negation of S leads to an impossible situation. So this is the basic idea of how you follow, or whatever process you follow in a proof by contradiction. Start with assuming the negation, do some calculations or do some assumptions to reach a point where there's some kind of a contradiction. And when there's such contradiction, then prove that S must be true because negation of S leads to some contradiction, right? Okay. Now, when to use it? These are just some additional points that I would suggest you can keep in mind. When direct proof is difficult, but assuming opposite leads to a clear inconsistency, right? So the basic point is that maybe when you think about the direct proof, right, you're trying to think of solving a problem by direct proof. Maybe it's not giving you a clear idea of how you can do it, right? So for example, when I'm trying to prove that if n is even, then 2n is even, there's an easy process that I can process in my mind of how I can do it. But in this case, there is no clear way I can think of in the direct way. But maybe you can find out some inconsistency if you assume the opposite of it, right? So that is exactly what you're trying to look for. And again, this is not something that you will understand from the very beginning, right? So the more you do the practice of these type of questions, the better you will understand how this works, right? So a quick suggestion would be look for more and more questions on proof by contradiction and of different types, right? So that would be a huge help. Now, second, commonly used for irrational proofs, uniqueness proofs, and non-existence proofs, right? So just like I said, when we are trying to prove something is irrational, uniqueness, maybe something is unique, and non-existence, that something does not exist, right? So these are the basic types. You can keep this in mind again. So maybe when you encounter such type of proofs, right, it would be a clear idea in your mind that you're probably supposed to do it with contradiction. So I hope you understand the basics of what is proof by contradiction and what is the logical flow we solve a proof by contradiction. Now let's take a look at two basic examples, and then I'll be giving some questions for you guys to solve. Okay, so let's take a look at two examples, starting with, let's try to prove that the square root of 2 is irrational, right? So let's try to understand what is the logical flow that we are going to take. I'm going to make the assumption of the negation of the statement, right? That is, I'm going to assume that square root of 2 is in fact rational. Once I make that assumption, I'll take a look at all the things that I can gather, right? All the equations that I can form, and then try to prove some kind of a contradiction. When I reach that contradiction, that's when I can say that I have proved the original statement. So let's take a look at how this works, right? So let's assume square root of 2 is rational, right? So think about it, right? If we know a number is rational, then it has to be of some form a by b, right? Where a and b are a would be the numerator and b would be the denominator, right? And what I can say is then square root of 2 is of the form a by b, right? I hope you understand this notation in this case. In this case, a would be the numerator, b would be the denominator, where a and b are integers and in okay. Let's try to understand this statement. I made the assumption that square root of 2 is rational, right? And rational numbers have some form a by b, right? So what I did is I say that then square root of 2 has to be of some form a divided by b, where a and b are integers and a divided by b is in the simplest form. Now, what I mean by the simplest form is the fact that I cannot simplify this equation further. I cannot simplify this rational number further into any further smaller number, right? So think about it. If I say 4 by 2, then this is not in the simplest form, right? I can cross this with the value 2, and this would be the simplest form of this number, right? So the basic idea is that every number, every rational number is of the form sum a by b, where a and b are integers and in the simplest form. Now, let's try to look at further what we can do with this equation. So until now, I have this point that square root of 2 is equal to a divided by b. Now, this is going to be extremely helpful for us, right? First thing, what I can do is I'll make the assumption, or I'll square both the sides, right? So let's first square both the sides. Squaring both the sides, what I get is I get 2 is equal to a square divided by b square, right? So square root of 2 is equal to a by b. Squaring, I get 2 is equal to a square by b square. Now take a look at what I'm going to do with this equation, right? What I can do is I can take this b to the other side, which gives me 2b square is equal to a square. Okay. Now let's try to understand what is the conclusion from this equation we get. Now, since a square is of the form 2b square, then that basically means that a square is an even number, right? If you know, even numbers have the form 2p or 2k, where k is some integer, and odd numbers have some form 2k plus 1, right? And in this case, we find out that a square has the form 2b square. So the conclusion is a square is even. And if a square is even, then think about it, right? Then a also has to be even. If the square value is even, then the original value also has to be even. Thus, a is even. Okay. So this is the conclusion that I come at from this point. Now you might be wondering, how am I able to solve this question and make all these assumptions in the right way? Just like I said, the more questions that we solve, the better we get at solving these type of questions, right? But they usually have a very general flow of solving such questions. Okay, so a square is even, thus a is going to be even, and this is the conclusion that I've made. Now, since a is even, right? Think about it. If a is an even value, then it has to be further of some form 2k, right? Where k is some integer. So, since a is even, then a is equal to some 2k, where k is an integer, right? I hope you're able to understand until this point, right? I took the equation square root of 2 equals a by b, squared both sides, and came to the conclusion that a is even. Since a is even, then I come to the fact that then it has to be of some form a is equal to 2k, right? Now, what I can do is I can take this equation, the first equation that I found, and I can replace this a square with the value 2k. So let's see what happens, right? I'll just move this on this side. So I get 2b square is equal to 2k square. We are making the assumption a is equal to 2k, right? So since 2b square is equal to 2k square, if I try to solve this equation, I get 2b square is equal to 4k square. And if I try to solve this further down, I get b square is equal to 2k square. Okay. So let's try to understand what is the conclusion from this. This is very similar to the equation that we found in the case of a square, right? When I came to the equation that 2b square is equal to a square, that gave me the conclusion that a square is even, which further results in that a is an even value. But then again, when I solve for b square, this also gives me the similar conclusion, right? That b square is even and b is also even because it is of the form 2k square. So what this means is that I write down this equation as 2. Okay. Now I'm going to tell you about everything that we did, and I want you guys to pause this video for 5 to 10 seconds and try to figure out the contradiction that we have made. We have already made the contradiction, but we have probably not figured it out yet. So the first thing is we assumed root 2 is rational. That means it has to be of the form a by b, where a and b are integers, and a by b is in the simplest form, right? Simplest form meaning we cannot simplify it further. Then I took the equation square root of 2, squared both sides, and came to two different conclusions. One is that a is even, and the second conclusion was that b is even, right? Now, what I want you guys to do is pause the video and try to figure out what is the contradiction. Okay, so I hope you have figured out the contradiction. Now, let me tell you what is the contradiction, right? If you think about it, if a is even and b is even, and that means they're not in their simplest form. So think about it, right? If I have two even numbers, 2 divided by 4, or let's say I have 4 divided by 8. If I have any two even numbers, then I can simplify them further into smaller values, right? 4 I can into 2 into 8. This gives me 2 by 4. I can further simplify this into 1 by 2. So when I have an odd value and an even value, that's when it would be a simplest form, right? But in this case, we came to the conclusion that both a and b are even, and hence that means we can simplify both the values further. But if you look at the assumption we made the assumption that a by b is in the simplest form. That is, we cannot simplify it further. So the contradiction is that when we made the negation assumption, we came to the conclusion that we can simplify them further, but the assumption was that we cannot simplify it further, right? So I'll write it down to make you to help you explain it further. Yeah. So this is going to be the final answer. Right? Once again, just a quick summary of the entire question. We were supposed to prove root 2 is rational, right? Then we had made the assumption that root 2 is rational. Then use some equations coming to the fact that a and b are both even. Since a and b are both even, this contradicts our fact that a and b is not in the simplest form, right? And hence, my final conclusion is irrational. Now, if you're not able to understand this question, I would highly suggest that you look back at this question, or maybe you can find a lot of videos online on other YouTube channels where you'll probably find a better explanation to these type of questions, right? But I think having a good understanding of about this would really help you out. And one more thing, if you're still not able to understand it, the best way, in my opinion, would be to solve more and more questions by yourself, right? And I think that will make this proof by contradiction concept very clear. Okay, now let's take a look at another example where we need to prove there is no smallest positive rational number. Okay, now let's try to understand that there is no smallest positive integer, right? We're supposed to prove that there is no smallest positive rational number. So let's try to understand once again, right? We know from a fact that this is not possible, right? There's no such smallest rational number, just like there's no smallest integer, right? So in these type of questions, these are kind of very easy to understand. I'm going to make the assumption once again. I'm going to assume the negation of the statement, right? And then I'm going to show a contradiction from that statement. So if I look at this, let's assume that there is a positive rational number. There is a smallest positive rational number. I'm sorry, if you're not able to understand, this basically means positive, right? So I'll just say positive. I've just written it in the short form. So let's assume that there is a smallest positive rational number R. So making the assumption that there is a smallest positive rational number R, right? Now let R be equal to A divided by B, where, right? So if R is a rational number, right? If it's a positive rational number, then it has to be of some form A by B, where both A and B are greater than 0, right? Because it's a positive number. So now think about this, right? If R is of the form, let's try to construct another rational number, right? So let R dash, I'll make the assumption that this is a new number, right? So R dash is that representation. Let R dash be equal to R divided by 2. So what I'm doing is, I made the assumption that R is some rational number A by B. So maybe I can create another rational number, right, from this by making it R dash, which is equal to R divided by 2, right? This is another rational number. I'm not making any rules on my own, and I'm not violating any rules, right? So this totally makes sense. Now, if I think about it, then this is basically A by 2B, right? Now, since A and B are both greater than 0, then think about it, right? Dividing this by 2 makes this value smaller. So, since A and B are greater than 0, R dash has to be less than R. Think about it, right? Let's try to understand once again. I made the assumption that there is a positive rational number, which is the smallest number that we know, right? So let that number be R, which is of the form A by B. So I try to create another number, right? I'm not breaking any rules. I created this R dash number, which is of the representation R divided by 2. Since this is also a rational number, it is of the form A by 2B. But since I made the assumption that both A and B are positive numbers, it has to be that this number is less than the number R that we assume. But once again, right, we have reached the contradiction right now. The contradiction is that this number is smaller than R, but we made the assumption that R is the smallest rational number, right? Hence, we can say that there is no such positive number. There's no rational number which is the smallest that exists. So finally, I can say this contradicts the fact that Hence, hence there is no smallest positive rational number, right? I'm just not writing the final statement down, but I hope you understand that finally you are supposed to write the original statement that you were supposed to prove, right? So I've solved two type of questions. One is when we are supposed to prove something is irrational, and second one is that there's the non-existence of something, right? So there can be a lot of questions based on contradiction, but just like I said, the more questions you solve, the better you will be able to understand of what type of proof you're supposed to use. Right now, decide to take a look at another type of proof, but this is the easiest one, which is going to be the counterexample. Okay. Now, let's try to understand what is a counterexample, right? This is the easiest type of proof that you will come across, but sometimes it can be difficult to find the counterexample, right? So, what is a counterexample? It is basically a single example that disproves a universal statement, right? So, what usually happens is that there is some kind of a claim, and in order to prove that claim is wrong, we just give a counterexample to it, right? And I think throughout the history in science and in mathematics, there have been so many claims that people made, but somebody gave a counterexample to it, right? And that's how we made better proofs and made better claims, which in turn made universal rules, right? So this is also one of the important type of rules, but very easy to understand that we are just supposed to find a counterexample. So let's take a look at the example one. Let's say I claim that all odd numbers are prime, right? Let's say I'm a scientist. I'm trying to claim that all odd numbers are prime, right? And you come across and you're saying that this is not true. And in order to prove that, you just need to give an example for me, right? And you come up with the counter example that 9 is odd but not prime, right? Because we know that 9 is a multiple of the number 3. So he gave a counter example, and this proves that all odd numbers are in fact not prime. Let's take a look at another example, right? So let's say I make the claim for all x, which are elements of the real numbers, x square is greater than x, right? I'm making the claim that for all the real numbers x square has to be greater than the value x. So I want you to pause this video for some time and try to find a counterexample to this statement. So I hope you were able to find a counterexample. The simple counterexample would be, so zero for x equal 0, x square is equal to x. So I made the claim, somebody made the claim, let's say x square is greater than x. But if I consider the value of x is equal to 0, right? In that case, x square is equal to x. And that basically means that they're not greater than equal to each other, right? So another counterexample that we can do. Another type of proof that you can come across is when you're supposed to find an example, right? So let's say I, instead of this point, I make the point that all odd numbers are not prime, right? And in order to prove that, I can maybe give an example that there are in fact a few examples that exist, right? That odd number is a prime. So for example, 3 is a prime number. Again, I can do the negation of this and try to find an example in that case. So both of these cases are possible, but this is the general counterexample is the general type of proof that we cover. But the basic summary is that you're given some kind of a universal statement, and in order to prove that wrong, we try to find a counterexample to it, right? So I hope you were able to understand all these questions. Now I'll be giving a bunch of practice questions on the board for you guys to solve. Okay. So I've given these three questions on the board. I'm just giving you a hint. The first two are supposed to be done using contradiction, right? In the second one, I've already mentioned it, but the first and the second are both supposed to be done with contradiction. And the last one is where you're supposed to use the counterexample, right? So these are not very tricky questions. They just need some kind of I would say you just need to put some kind of a focus into it. But I think you'll be able to solve these questions, right? So that's it for this video. In the next lecture, we will be starting with the most important type of proof and the most difficult one, which is going to be proof by induction.